Hey everyone, today we're going to dive into one of the most powerful ideas out there. How can we possibly understand a massive group, like a whole country, by looking at just a tiny, tiny piece of it? This is the magic behind statistics.
So let's just jump right into this central puzzle. How on earth can a poll of just a couple thousand people tell us what millions are thinking? Or, how can a scientist figure out a whole species just by studying a handful of them? It really feels like it shouldn't work, but it does, all thanks to some really brilliant principles.
Okay, first things first, we got to get our language right. The challenge is always the same. We want to know about the whole shebang, but we can only ever look at a small part.
So let's define our key terms with a super simple analogy. The population is everything we're interested in, the entire ocean. And the sample? Well, that's the small piece we can actually get our hands on. Just one bucket of water we pull from that ocean.
Now, let's add two more critical words to our vocabulary. The parameter is the real true value we're hunting for, like the actual overall saltiness of the entire ocean. But of course, we can't measure that directly, so we use an estimator. That's our best guess, and we calculate it from our sample. It's the saltiness we measure in our bucket. The whole game is to make our estimator get as close as possible to that true parameter.
So how do we get a good guess? Well, our first big clue comes from a really simple idea, just doing it over and over. The real magic starts to happen when you repeat something again and again and again.
This brings us to something called the law of large numbers. And honestly, it's the bedrock of all this stuff. It's a simple but really profound truth. The more data you collect, the closer your sample's average gets to the population's true average. It's like the more you look, the clearer the picture becomes.
Let's make this really concrete. Think about flipping a coin. We know the true parameter, right? The probability of getting heads is exactly 0.5.
But if we only flip it, say, 10 times, we might get 6 heads. Our estimator, 0.6, is a little bit off. With such a small sample, luck and randomness play a huge role.
Okay, now let's do it 100 times. We might get 52 heads. Our average is 0.52. See, we're already getting much, much closer to that true value of 0.5. And what if we do it 10,000 times? Well, now our average might be something like 0.501. At this point, our guess is practically identical to the real thing. All that random luck has just kind of canceled itself out.
So the crucial takeaway here is this. The more data you have, that bigger N that statisticians are always talking about, the less your results are going to randomly bounce around. A bigger sample makes your guess way more reliable.
But the law of large numbers is really just the beginning. What happens if the thing we're measuring isn't a simple 50-50 coin flip? This is where we get to one of the most beautiful and, frankly, mind-blowing ideas in all of math.
So let's say our real-world data is, well, messy. Imagine you're tracking the number of customers who walk into a store each day. Some days it's dead quiet, other days it's just chaotic. The data is all over the place, totally lopsided, and doesn't look predictable at all.
Now, we're going to run a little experiment. We'll grab a random sample of, say, 30 days and calculate the average number of customers. We'll take that one number, that one average, and plot it. Then we do it again. Another 30 days, another average, another plot point. And we're going to repeat this thousands of times.
So what happens when we plot all those thousands of individual averages? What pattern do they make? This is where the magic kicks in, and it's called the central limit theorem. And it says something amazing. No matter how weird or messy your original data is, the distribution of the sample averages will always form a beautiful, predictable, symmetrical pattern.
And there it is, our totally chaotic customer data, once you sample it and average it over and over, produces this, a perfect bell curve. This is unbelievably powerful, because the bell curve has all these well-known mathematical properties that let us calculate probabilities and make really precise predictions about the true average.
Okay, so we know that samples are powerful, especially big ones. But when we get our one sample and calculate our one guess, how do we know if it's any good? How do we actually judge the quality of our estimator?
A really great estimator has two things going for it, low bias and low variance. Think of it like an archer. Bias is about accuracy. On average, are your arrows hitting the center of the target? An unbiased estimator is one that, on average, is dead on. Variance, on the other hand, is about precision. How tightly clustered are your arrows? An estimator with low variance gives you super consistent results every time you take a new sample. What we want is the perfect archer. accurate and precise.
So this leads to a really practical question. How do statisticians actually find these great estimators? I mean, they don't just pull them out of thin air. They follow these systematic procedures. They're almost like recipes, designed to give them the best possible guess.
We're just going to quickly touch on two of the most famous of these recipes, the method of moments, or MOM for short, and maximum likelihood estimation, or MLE.
The method of moments is probably the most intuitive way to go. It's based on a really simple matching idea. It basically says, you know what, the average I just saw in my sample, I'm just going to set the population's theoretical average to be equal to that. It just makes the theory match the data you actually have.
Maximum likelihood estimation. Now this one is really clever. It kind of works backward. It looks at the actual data you collected and asks a brilliant question. What would the true parameter have to be to make the data I'm holding in my hand the most likely possible outcome? It's a powerful way of letting the data tell you what the truth probably is.
So let's just pull this all together. These concepts, samples, populations, the law of large numbers, the central limit theorem, these clever recipes for guessing, this isn't just abstract textbook stuff. This is the actual engine that powers modern science, political polls, marketing tests, pretty much every data-driven decision that gets made in the world today.
But, and this is a huge but, this whole amazing, powerful system of guessing the whole from a part is built on one single, absolutely critical assumption, that our sample is a fair, random snapshot of the population. Because if our bucket of water is drawn only from a polluted part of the ocean, all the fancy math in the world isn't going to tell us anything about the clean parts. Which leaves us with a final thought. What happens if our sample is biased from the very start? That, it turns out, is the one flaw that no amount of statistics can ever fix.